about what STM can do. So here's one of the early days, the triumph, if you like, of STM, was that people have been studying this silicon surface, 111, so-called 1117 by 7 surface, and for 20, 30 years, and nobody knows, really, nobody knows what is the structure of these, and what do you, and people see this from low energy electron diffraction. So this is a typical lead pattern that you see. This is my lead pattern. So what do you see in the lead pattern? You see this spot. I think I showed you this lead pattern when we were talking about lead before. You have this hexagon, if you like. This is a 0, 0 spot. You have hexagon, and then in between you have 6 dots. Basically 7 equal spacing between the strong spot, which is your spot, and then you have this weaker spot. The weaker spot corresponded to reconstruction, surface reconstruction. And this is one of the riddle, if you like, one of the puzzle, the main puzzle in surface science for 20 years that people have been trying to solve this beautiful lead pattern. What can give you this pattern, okay? And Takayashi in Japan had looked at all this data, not just from lead data, but other information that's XF and so forth, and try to come up with a model. And what he got is this pattern. Okay, so you can see 7 by 7. If you look at the diamond structure of the 7 by 7, it's a very simple. It's a hexagon, right? If you look at the diamond structure, go back to my crystal structure part. But Takayashi and company have figured out, well, maybe it is like this. Maybe it's so-called so he proposed a DAS model. So it stands for dimer at atom stacking fault. Dimer at atom stacking fault. So you have a dimer wall. So these are dimer. You can see this silicon, this dimer wall all around surrounding here. At atom, these are the at atom. Okay, so there are 6 at atom on. So this is 2 halves. There's the folded half and the unfolded half look symmetrical, but they are not quite symmetrical. So they are at atom. There's rest atom. These are the so-called rest atom. And you have dimer rows. So you have dimer surrounding this half unit cell. And the 2 halves are not the same because the folded half, this atom is called folded half because there's a stacking fault. Because when you build this structure, somehow the surface stacked in the wrong way. Ideally, you want this atom not overlapping with any atom in the underlayer, whereas on the folded side, this atom actually overlap with the second layer overlap with the 5th layer, right? The 5th layer like this. You can see. So that's a stacking fault in here. And for the longest time, people don't know whether is that right, is that wrong, what happened, can we see this? And one of the very first tests of STM, of course, is to solve this puzzle. And here it is, right? So this is the picture. If you look at the stacking, the AS model, let me try to position them. Let me turn it around like this, right? You can compare a little bit better. So you can see, if you turn it around, you can see 6. So here's my unit cell, right? Here's my unit cell. So 6 at atom, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, right? And then you have other at atom on the other side, 1, 2, 3, 4, 5, 6. So the brighter side is the folded half. The less bright side is unfolded half. And you can see the rest atom. If you have good enough microscope like the one we had, you can see, you can make out. So for example, there are 3 rest atoms. This one, and this one. They are in between the triangle. So you can see this one are the at atom. So in between, you can see a little density here, fuzzy density, and that's the rest atom. Okay. So it's power, right? This is power because you can see you can resolve atom with STM, and people get extremely excited by this. And this is one of the puzzle that people find. Yes?
What do you mean by folding here? What do you mean by folding here? The bottom right side is folded, right?
Yeah, it's stacking, it's so-called stacking fault. Stacking fault. The reason why it's stacking, let me go back to this. Stacking fault is that ideally if you stack your 111 surface, there should be this layer should not be directly on top of another atom. You should not be stacking on top of it, right? You can see, but whereas this one, this layer is stacking directly on top of the fifth layer. Okay, so this is called stacking fault. So you can see here, you see this little dot here. This little dot represents to this atom, right? So this dot represents. So there's no fault on this side. There's no fault. Whereas on this side, because this one is covering this one, you don't see this dot on this side, right? So this is called stacking fault, and you can see it by the differences in intensity in the STM image. So here you go, right? So this is a triumph in STM, in science, right? You invented a tool, and now you propose a model, and if the model works, it's amazing, right? So you can actually see atom, right, like this. You not only you see the two differences, you can see always like that. This is always higher in the intensity than the other half. You see? It's always like that, right? Beautiful, beautiful stuff, right? And what are these? Well, these could be dirt, we don't know. What are these? This could be hydrogen atom, right? So there's a lot of ambiguity. Even though you resolve this, this puzzle, there's a lot of ambiguity along with this. Okay. Now, in your assignment, I think, you are supposed to, I think one of your assignments may ask you for this 5x5 image. So this is my 7x7, and you can actually build a larger unit cell, 9x9, or smaller one, 5x5, like that. So I think one of the questions asked you to construct the 5x5 unit cell, which is easy if you know about how to construct this.
So what considers it 7x7? Where are the 7?
Yes, so 7x7 is remember, 7x7 is a lead notation. Okay, so what that means is that you look at the lead pattern and you see 7 spots across. Right? This is like the Woods notation. So you look at I don't have it with me here. You look back in the old lecture note, we have shown the 7x7 lead pattern. Okay, so this notation is the lead pattern. The real space model, right, is like this. Right? This is why it's difficult to come up. How do you get from this to this, right? I mean, this is there's a lot of work, and the Japanese group, they are theoreticians actually. They look at all the data, all the structural data before STM come along. They have proposed this. I think in the paper come out in 1982 or earlier like this. So they are theoreticians, Takayashi. They come up with this idea. It's called DAS model, and there was some criticism about this because they say, hey, I can propose other things and I can generate this. But the triumph was that with STM they solved it. So one of the first thing they image once the STM inventor we get it working is that they take a 7x7 surface inside and see what is a 7x7, and they find Takayashi's group was in fact correct. So they come up with this. Right, so that's a real triumph, I would say, in science, that you have a theorist group and then you have experiment verifying the theory, and you do chemistry with this. Because why is this so interesting? Well, because if you read this paper, right, you will understand. I encourage you to go read this paper. You understand why you need 7x7 is that the 7x7 reduce the number of dangling bars of the surface, because the reason why the surface